So first let us look at what exactly is shear force. So we have a beam over here. On the top we have it in a 3D view, and in the bottom we have a 2D view of the same beam. Now a shear force is any force that acts parallel to the cross section of the beam. So this is the cross section of the beam that I have drawn in pink. Any force which is parallel to it, right? Parallel to that cross section is going to be a shear force. So something like this is perpendicular to the cross section, so this is not shear force, but this is parallel, so this is what we call as shear force. Now that force can also be like this, or like this, or even like this, okay? But since we are dealing in a 2D plane, we will not be using forces like this. So we will have either a vertically downward shear force or a vertically upward shear force, like this. What is the effect of a shear force? So as we know, longitudinal forces actually create some sort of elongation if it is tensile in nature, and if it is compressive in nature, then they will make the body contract. Now what exactly does a shear force do? So for that, let's come to this 2D figure over here. Now let's say that this is the cross section and we put a shear force like this on it, right? Now the effect of this force will be to shear off the right hand side of this beam. So the right hand side will tend to move downwards because of this shear force, right? Now it is important to note that the right hand side is the one that will get sheared off, not the left hand side. Why not the left hand side? Because on the left hand side actually you can see that this is a rigid support over here. So this support will also have some sort of an upward reaction over here, which is supporting this part of the beam. This part of the beam is completely free, so there is no load on this part of the beam until this point, right? And so the right hand side will actually tend to get sheared down. Now that we know what shear force is, let's now talk about the shear force diagram. What exactly is a shear force diagram? So for that, we'll just draw a line over here. So this is called the axis of the shear force diagram. So now I have broken this beam into a number of elements, and we will be assuming that each of these elements is nothing but a point, right? So if this is the observer, if this is you, for example, if you're sitting on one element and then you go to the next one, that essentially means that you have just gone 1 point to the left, right? Now there's something special about you. You can't see to the left of you. You can only see towards the right of you. You can only see towards your right, and you move one element to the left at a time. Now starting from here, you enter the beam like this. Nothing. Move to the next element, still nothing. Move to the next element. You cannot see any forces at all. You finally move to the right of this force over here, and suddenly you can see this force. How will this look in a diagram? So up until this point, okay, up until this point there is nothing. So on the graph, on this axis, this will be at the baseline, right? Now that you have this force, this downward force, your graph will suddenly jump. It can go up like this, or it can go down like this. How do I know if it goes up or down? Well, the convention is if the shear force is positive, then it will go up, and if the shear force is negative, then it will come down. Now how do we determine if the shear force is positive or negative? For that, we need to look at the sign convention. If the shear force is such that it is trying to move the right hand side of you downwards, then it is taken as positive. On the other hand, if it is trying to move it upwards, that will be a negative shear force. So the reason why I drew so many elements is to make it absolutely clear that you can only see this shear force, or this shear force will only reflect in the graph once your point of observation has moved to the left of it. Many people get confused when they draw this beam like this, for example, and this is the shear force, right? And they are observing it from this point and then coming here to here to here to this point itself. They get confused as to whether this shear force is trying to move the right side downwards or is it trying to move the left side downwards, right? And the mistake that they make is they try to analyze it from this point itself, right? They try to observe this force from the point on which the force is acting. That is not the right concept. You will have to move to the left of this force for this force to be reflected in the shear force diagram. And now from the sign convention that we just learned, we can see that we are over here. And so this shear force is essentially trying to move this element downwards. Right side downwards means a positive shear force. And so the shear force will look something like this. And then it will continue till when? Till the last point over here. So it will continue till here. But then what happens? The beam has ended, but what about our graph? What is going to happen? Well, if you see, the cantilever beam actually will provide a reaction force over here. But by then, where is your observer? Your observer has to move to this portion over here, right? And now, with respect to your observer, if you see, this force is actually trying to move this element upwards. And hence, this is essentially right hand side upwards or right side upwards, which means that the shear force now will be negative. And so starting from there, it will drop down to the baseline. Why will it drop down to the baseline? Because here, let's say for example, the magnitude of force was P, right? So over here, this length is essentially P, right? Whatever scale we are using on the graph, this length is going to be equivalent to P. And now this force, obviously, to maintain equilibrium, this force also has to be P. This reaction force has to be P, right? And so from here, this will decrease by an amount of P. This is actually the entire concept of a shear force diagram due to a point load. Now we will move on to something called the UDL. So let's say we have a uniformly distributed load on this cantilever beam, and let's say that it ends at a point like this. Okay, and then let's say for example, to make things a little easier or make things a little more interesting, let's say for example that there is a point load over here as well. Okay, how about now what exactly happens to the shear force diagram? This is my point of interest, so I'll draw a dotted line over here, and this is also a point of interest where the UDL is ending. As soon as the observer is on this element, he is seeing some load, right? Now what about when this observer moves towards this load? He is actually seeing the load on this element plus the load on this element. He is seeing essentially 2 times the load that he was seeing when he was on this element. Now when he moves here, he is going to see it 3 times, 4 times, and then when he moves again, he is going to see this 8 times. But now this becomes constant. And obviously if you see that like if you place him anywhere over here, he's only seeing the loads on the right hand sides. So again, these loads are tending to shear the right side of him downwards, right? So the sign will be positive. So when he is over here, the shear force is 0. Then eventually it starts growing, and it starts growing linearly. So we will essentially get a straight line like this, right? So this is a straight line. And then when my observer is over here, now it becomes constant, right? So this line again will become constant up until this point. And then there is another shear load over here. When the observer moves over here, he is seeing this entire load at once, right? So from this point, actually this will rise up just like this, right? Whatever the magnitude of this load is, say for example if this is P, then this will be rising a distance of P. And then again over here it is constant again till he comes here, right? So constant, let me draw a constant, boom. And then when he comes over here, he can see that there is again another reaction force on this side of the cantilever beam or the support of the cantilever beam. And so all of this will drop down to the baseline. Why will it drop down to the baseline? Because the load on this point over here is going to be the sum of P and the sum of the entire load that is there in this position. So essentially you can understand, I hope, that this entire load is represented by this gap over here. So this UDL over here, this is not going to be characterized by a single magnitude like P. It is essentially some mass spread over a given length. So this will be represented by mass per unit length. Oftentimes this is denoted by the letter W, and the unit of this W is often kilonewtons per meter. If we look at this part of the triangle now, okay, whatever the length of this is, say for example this is L1, okay, let's say that this length is L2, and let's say that this is L3. Okay, great. So this triangle is actually going to be L1, and this length over here is going to be this entire load, right? So what is this entire load? That is mass per unit length times the length, which is W L1, right? So that is the shear force diagram due to a uniformly distributed load. Now if this load was uniformly distributed through the entire beam, this graph would have been something like this. So a straight line all the way till here. Now obviously I will have to draw this axis a little lower in order to make that possible, but that is how it would have looked. But what I did over here is I combined a point load as well as a uniformly distributed load, right? You can also have a situation like, for example, if there is a load, for example, there is a load P2, for example, right over here in between this uniformly distributed load. So what happens in that kind of a case is that in this point over here in the diagram, when your observer reaches from here to here, say for example, till here he was seeing the load gradually increasing, and here over here, as soon as he comes here and sees this load, he will look and find a sharp increase over here. So this, he will find something like this, and then as he continues to the right again, this load will again become increasing gradually. So this is how you can draw the shear force diagrams for uniformly distributed loads and point loads combined.